All right, I think we can go in and get started. It looks like the number of people joining have been kind of stabilized. Good evening, everybody. Thank you for joining. This week, we're going to have a talk on radiation exposure with Dr. Buckey, and then we'll end the night with a student presentation by Ryan. So without further ado, Dr. Buckey, I'll go ahead and make you co-host.
Okay, great.
There you go. Should be good. All yours, Dr. Buckey.
All right. There we go. Okay. So we're going to talk a little bit about a radiation exposure, which is actually probably one of the more limiting things for long duration space flight. And it's not necessarily because of the reason you might think of, let's say, developing cancer. It's more because of the unique nature of the radiation that you get in space. And we're going to talk a little bit more about that in a moment. So we're going to talk about two main kinds of radiation that you get in space. The radiation that we're sort of familiar of, the acute radiation exposures like we hear about from atomic bomb blasts or from medical exposures. And then we'll talk about galactic cosmic radiation, which is sort of something that we have very well under control here on Earth, but is more of a problem when you're out in interplanetary space. So I just want to start off with a little story. I don't know if you are familiar with the novel Space by James Michener, but in that novel, he presents a fictional scenario that could have happened during the Apollo program of missions to the moon. In the novel, astronauts are on the surface of the moon when the radiation from a solar flare arrives and they receive fatal doses of radiation. And it was based on the fact that around the time that the Apollo missions to the moon were happening, there was a very large solar flare. And if indeed astronauts had been on the surface of the moon outside of the spacecraft at that time, they would have gotten a lot of radiation from this solar flare, which is mainly protons. And it would have been, for them, it could have been fatal because out in the spacesuit, you don't have much protection for radiation. So the radiation can be an immediate threat in the space program. However, to start thinking about radiation, I think it's important to get some sense about scale, because in the biological realm, we're usually used to thinking about the size of cells and molecules. Here, we're talking about the things that are, down at the atomic level. And just to give an example of this issue of scale, I'm going to do a little power of 10 exercise where this is a picture of the nucleus of a leaf cell, and that's at 1 micrometer, 1 micron. If we go in, magnify it by 10, so that we're at the 100 nanometer scale, we can see the chromatin. If we go another power of 10, at 10 nanometers, you can see the individual DNA strands. Another power of 10, you're down to seeing individual building blocks of the DNA. But then another power of 10, you're down in the outer electron cloud of a carbon atom. Another power of 10, you're just in the inner electron shell. Another power of 10, you still haven't reached the nucleus yet. And then it takes 3 powers of 10 pretty much to go from the inner electron shell to the nucleus. So there's a lot of free space in matter. And so when we're talking about the atomic level, and we're talking about things like protons or the nuclei of atoms coming through tissue, it's possible a lot of times that it may not hit anything. But because we're talking about something at a very small level, a really tiny level. By comparison, if you want to look at 3 powers of 10, if this is Earth's orbit here, and you go 1 power of 10, you're down at the moon, and then it takes you about 3 powers of 10 from looking at Earth's orbit to actually being in Earth's orbit. So just a sense of the scale that we're talking about when we're dealing with things like radiation, where we're talking about stuff at the actual atomic level. The radiation that we're familiar with here on Earth, like the radiation we deliver for medical purposes, is all part of the electromagnetic spectrum. And let me activate the little pointer thing here. Oops. So like we're familiar with ultraviolet light giving us a sunburn. And but if you think of really high frequency light, that's when we're starting getting into X-rays and gamma rays. And you do experience some of that radiation in space. It's not necessarily the most primary thing we're concerned about. And what does radiation do? Well, we tend to call this kind of radiation ionizing radiation, which means that if it hits something, it creates ions. And this picture kind of gives an idea about what happens. So if radiation gets into tissue, it's not that likely that it's actually going to hit DNA because most of us is water. So if it's going to hit anything, the more likely thing that it's going to hit is a water molecule. And if it does that, it can form free radicals. And then an important consideration is that it needs oxygen to help stabilize those free radicals. And it's those free radicals that can then cause damage to DNA. So, so one thing to think about is that radiation, although we tend to think of it as a physical thing, a physical, amount of energy damaging DNA, it is often more chemical damage, that it's this chemical damage, this production of free radicals that is actually causing the tissue damage when you give radiation. So you can think of radiation as actually kind of chemical damage from the radiation forming these free radicals. Radiolysis of water is what's happening, or that just means breakdown of water by radiation. So it produces hydroxyl radicals. The hydroxyl radicals react with oxygen and produce other oxygen-based free radicals. A fun fact is that it's important to have oxygen in the tissue for radiation to really work well. So, for those of you who are involved in radiation oncology or giving radiation to treat cancer, one of the problems with treating cancers with radiation is that those tumors have a low oxygen level, which makes them relatively resistant to the effect of radiation. And so that's why it's often given in fractions, so that each day that the radiation is given, hopefully it's hitting a different population of cells that have enough oxygen for the radiation to do damage. And as mentioned, if the free radicals interact with proteins or DNA, they can produce significant damage. And I guess the estimate is that probably about 2/3 of the damage produced by X-rays or gamma rays is mediated by these free radicals. So basically, it's chemical damage. How do you measure, the effects of radiation? Well, what we often use is units of either gray or sieverts, which says SV up here. And that's the amount of sort of energy per kilogram, or joule per kilogram. One gray is 1 joule per kilogram. And a sievert is very much similar to the gray, except it takes into account the different quality of the radiation to produce biological effects. And just to give you a sense of what the radiation does is, these are doses. These are whole body doses. So if you got this much radiation all at once, like would happen with an atomic bomb blast, the main things that you see initially are these GI and effects from the bone marrow. And that's because the GI tract and the bone marrow have a lot of rapid cell turnover. And so they're the most sensitive to these acute radiation exposures. As it goes up, you start to see more effects on the bone marrow and the GI tract. Then you really don't see problems with the central nervous system until you get up to really high doses. And that's because the central nervous system, the cells there are not turning over very rapidly. And so they're fairly radiation resistant. So, so this is the kind of thing that would happen if, let's say, this solar flare came along. You would definitely see it in gastrointestinal system symptoms and problems with the bone marrow. Only later on would you see problems with the central nervous system. So, but that's just one kind of radiation that we're talking about here. This high energy light, like ultraviolet light or X-rays, and how that distributes energy in tissue is sort of shown in this thing on the left, where if you're having X-rays, each cell gets a little bit of radiation. So if you have this amount of energy, 10 milligray, it's distributed among all these cells. So each cell gets a little bit, and if you increase the dose, then each cell gets a little bit more. But what if instead of like these photon radiation, this high energy light, we're using neutrons, which is like a particle? Well, here the particle is stopping in the tissue and it's only hitting a few cells. So all the energy is being deposited in those few cells. And if you have a higher energy neutron, it'll affect more cells, and those cells may also get some more energy. So you can see that this is more likely to do severe damage to the cells that it hits, whereas this is going to do sort of a diffuse damage. And that's important when we start to think about galactic cosmic rays. And I'm going to show you a brief video clip from a video from the 50s about, it's called The Strange Case of the Cosmic Ray. And it describes what these cosmic rays are, or the galactic cosmic rays. So here's a little clip here.
And hurtling through space at unholy speeds, atomic bullets from beyond the beyond, crashing into us with almost the speed of light.
And when he says crash, he means crash. These cosmic ray babies crack into us with energies of more than 1,000,000 billion electrons.
So I don't know if the sound came through, but anyway, they're describing that these galactic cosmic rays do come from beyond the beyond. They're supposed to be thought left over from the origin of the universe. They come from all directions. It's not like getting X-rays in the sense that it's not a concentrated amount. It's a small amount of radiation given continuously. And each one of these galactic cosmic rays is basically a nucleus. So it could be a proton or it could be an iron nucleus. And so that's a lot more of a substantial thing than, let's say, a photon. So, and if that launches itself into tissue, it can create this, what is called an ionization tract. So this is a picture from a balloon flight. And looking at, I think on the left here, this is an iron nucleus, and 90, that would be uranium. Anyway, this is a heavy ion depositing its energy in a film emulsion. So you can see that if you imagine your central nervous system is where this energy was being deposited, that might do some serious damage. Something that, taking antioxidants might not be good for, right? So taking antioxidants might be like taking vitamins to combat a gunshot wound. It's really doing some damage along this tract. And this is sort of a graphic of why we don't worry that much about galactic cosmic rays here on Earth. And there are two key factors. One is, since this is a nucleus of an atom, it's charged. And since there's a magnetic field around the Earth, a lot of these galactic cosmic rays are deflected. And so that really reduces the amount of galactic cosmic radiation we have here on Earth. The other thing is that because of the atmosphere, a lot of the cosmic rays that do make it to Earth end up having interactions in the atmosphere. And this is sort of looks like those little ionization tracts, except it's in the atmosphere, and produces secondary radiation. So as the galactic cosmic ray comes in, it hits other molecules, which then creates other radiation that we experience here on Earth. And I wanted to show you a little picture of what that looks like. This is a cloud chamber. I don't know if you've ever done this as a science project or seen this, but what you do is you create a cold mist, and then with that you can see the tracks of the ionization tracks as radiation makes its way through the cloud. And let's see if we can play that. Oh, bummer. Well, I don't know what happened to my cloud chamber movie. Well, maybe we'll come back to it. But anyway, what you see is you can see right in front of you, you can see the ionization tracks of the radiation in the room that you're in hitting in, going out through the cloud chamber. But it's mainly secondary radiation, not as energetic as the original galactic cosmic rays. So how significant is this? Well, this is a chart of data from Curtis, who did a numerical model to try to estimate how many cells and cell nuclei would be hit by galactic cosmic rays on a simulated 3-year Mars mission. And actually, it turns out to be pretty significant, that just being out in the spacecraft with the galactic cosmic rays over time, you're going to get hit in the central nervous system quite a bit. And so you start to worry about what does that do to brain function over time. And data from rodent studies and other animal studies do suggest that there is a cognitive effect from this, that over time you can see cognitive effects and effects on performance from this low rate galactic cosmic radiation hitting the central nervous system. And as I mentioned, it's probably not the kind of damage that would be amenable to some sort of radiation countermeasure that you could take by mouth. That probably the solution is more using shielding. But there is a problem with shielding. So here, when we're using X-rays for medical imaging, people put on a lead apron, right? Because the lead is very dense and it's very good at preventing photon radiation for getting through. So if you shield yourself with lead, you'll do well as far as preventing yourself from being irradiated. That's not so effective when you're talking about galactic cosmic radiation, because remember, these are the nuclei of atoms traveling at incredible speeds and having really high energies. So if they come into the lead, is the likelihood they're going to interact with the nuclei they find in lead and create secondary radiation. So to creating alpha particles, gamma rays, different radiation that comes from the galactic cosmic ray hitting the lead. And it is actually the case that for a lot of shielding thicknesses, you would actually end up with more radiation in the spacecraft if you're using something like lead. You'd have to make it very thick before you could really start to defeat that. But some lead as a shield with galactic cosmic radiation might actually serve as a radiation amplifier rather than a radiation shield. Things that are less dense, things that include a lot of hydrogen items like liquid hydrogen or polyethylene plastic or water tend to be better choices for shielding for a spacecraft that's going to be on its way to Mars in interplanetary space. But it makes you wonder, is there another approach to this? Rather than using a huge amount of shielding to try to get radiation levels in the spacecraft down to an acceptable level, is there another way to do this? And is there a possibility, perhaps, of creating a magnetic field around the spacecraft? And this is a concept that was from an article by Werner von Braun, believe it or not, in 1969. And it's an idea that's been around for a long time. And the idea is, could you create a magnetic field around the spacecraft and use that to try to prevent the damage from galactic cosmic rays? And this is such a concept where they're visualizing a superconducting magnetic coil, which, by the way, didn't exist at that time. You couldn't really get a coil like that. And from that, create a magnetic field, which then hopefully could be used to deflect radiation. And these days, this may be an idea that's worth relooking at, because it is possible now to have superconducting magnetic coils. Although the level of the strength of magnetic field you have to use is pretty high, but some sort of toroidal spacecraft structure like this with an active shield would allow you to go through interplanetary space and not have to worry about ongoing damage from galactic cosmic radiation. So that's just my little intro to radiation for space flight. You got to worry about acute things like solar storms, or solar events. I didn't mention this, but you also have to worry about some of the electrons in the Van Allen belts. And then you also have to worry about galactic cosmic radiation when you're in interplanetary space on your way to Mars. But it may be something that really is more amenable to an engineering solution, something like this, than to a medical solution. And I'm hoping to see more progress in this as we move into the future. So thanks very much.
Thank you, Dr. Buckey. We'll open the floor up to any questions if anybody has any. If you have a question, just use the raise your hand function on Zoom. And then after questions, we'll go ahead and proceed with the student presentation. So if you have any questions, just feel free to raise your hand.
Hi, just more of a comment. I always thought the reason why the lead shielding was a bad idea was because of the weight. I had no idea. It's because of the potential to amplify the radiation. And I would believe that's a pretty common misconception among people.
So the weight is an issue. And the weight of a passive shield in general is an issue. So, when you start doing calculations of how much aluminum or how much, you wouldn't use lead, but how much liquid hydrogen or how much water, they have to be pretty thick. And so when you see these spacecraft designs that have these shields built in, they're pretty big, in order to get the radiation level in the spacecraft down to a reasonable level.
Cool. Thank you.
I should also mention that when you're on the surface of Mars, you do get some shielding, like you get the galactic cosmic radiation cut in half because the Mars is protecting you from the radiation that's coming from the ground below you. But you still get the other radiation. There's not much of an atmosphere to help. And so if you were on Mars, you'd have to spend a lot of time underground, which sounds like a whole lot of no fun after you've spent all that time and energy to get there, right? So I do think having a better solution is worthwhile for Mars exploration, because you don't want to be, who wants to go there just to live underground the whole time?
All right, Matt, do you want to ask your question?
Sure. I just had a question about the study that you mentioned regarding space radiation for the Mars mission. Did that study include both the trip to Mars and the effects while you're at Mars, or did it just include one aspect of the mission as a whole?
Yeah, so I'd have to go back and, look at it to make sure that I'm giving you the right info, but I think it went through the whole profile, getting there, staying there, and then coming back.
Okay, thank you.
The whole deal.
All right, Nicholas.
Hey, were there any what's it called, like measures or contingencies for like unexpected solar particle events during like Skylab?
Yes. Yeah. So the one of the key things is the ability to monitor that. So monitoring the sun to help to try to predict solar storm activity, and then to give the crew a warning when there is solar storm. So it takes about 8 to 10 minutes for the radiation to make it from the sun to the earth. So they do have some time to take some action. The idea is to try to create a storm shelter in the spacecraft. And they do this on the space station. There's some areas that are more shielded than others. And so people will try to spend time in those during a solar storm. And certainly if you're doing an EVA, you want to come inside, because a spacecraft offers a lot more shielding than a spacesuit does. So really for a solar storm, the key thing is don't be outside in your spacesuit. And then if you can, be in a little storm shelter.
Jane, go ahead.
Sorry, trying to figure out how to unmute. Hi, Dr. Buckey. So I remember from a previous presentation that the astronauts are limited to a total lifetime radiation exposure. And then there are some in the camp of that, it's kind of informed consent. They're already taking all these risks, and some in that, we should hard stop for their future protection. Like how do you feel about kind of balancing those two?
Yeah. So I mean, so there are two things. A lot of the limits for radiation exposure for astronauts is based on cancer risk. So and you have to keep in mind that your lifetime cancer risk is around 20-25%. without going into space. So you got to figure out how much more of a risk is reasonable. And I think they usually set that at like 5%, I think. And then they set a lifetime radiation limit, which tends to be something like 3 to 5 sieverts. I was just looking at this before. And if you remember you probably don't, but because I just showed it for a short time, but from that little chart I gave about, if you got like 3 to 5 sieverts all at once, that would be like a fatal dose, but you can obviously get radiation over your lifetime. You can get 5 sieverts worth of radiation over your lifetime at a low dose and probably be okay because we have the ability to repair DNA. So most of those things are based on cancer risk. It's really hard to know, because people vary in their risk of cancer to begin with. They vary in their ability to repair DNA. So, this overall guideline may not be applicable to everybody. There isn't really a risk based on damage to the central nervous system from galactic cosmic rays. I think we really don't have a sense of how much of a problem is that going to be and how can we limit that. So I often tend to worry about that more for a Mars mission than I do about the cancer risk.
All right, Jerry.
Yeah. Hi, Dr. Buckey. I was wondering, and my connection went out for a minute, so I apologize if I missed this, but I was wondering how accurate the forecasting of solar storms is. And, for example, would you have any or enough, let's say, of a warning if you were already engaged in risky activities like outside of the station, et cetera?
So I have to look to see how the technology has changed over time since the last time I looked. If you're here at Dartmouth, they have the physics department is very good on space weather, and they're very good at tracking solar storms, because solar storms are important here on Earth too, because they take out satellites and create problems in the upper atmosphere when the storms occur. But as far as how good it is, I don't know. You can usually give people about 8 to 10 minutes warning, which is enough, often is enough, depending on where you are. In the novel that I talked about, it wouldn't have been enough. If you were far away from the lunar rover and you only had, 15 minutes to make your way back, you might not make it.
Hey, Matt, did you have another question?
Yes. So I just remembered, I read an article, I think about a month ago, of a recent study that came out about ionized space radiation and how they stored some of the, I believe it was the white blood cell samples from some of the astronauts back in like the STS missions from like the late 1990s to like the early 2000s. And they found that there was like some mutations found after 20 years of like storing them in like a freezer. And I was wondering because I know your, Dr. Buckey, I know your STS-90 mission was focused on the effects of the nervous system and to microgravity. And I was wondering if you had any like relation to like finding how ionized space radiation affected the nervous system just on like a short duration level rather.
Yeah, so I don't have a lot of information how the radiation affects the nervous system on a short duration flight. In general, the nervous system is pretty tolerant to radiation of the photon type. So I wouldn't expect that much of a change. But it is true, you can see, in after missions, you can see a higher rate of chromosomal aberrations in peripheral blood samples than were present before people left.
Thank you.
Dr. Buckey, we have a question from the chat in reference to the idea of superconducting magnetic shields and small size experiments for proof of concept. Have you heard of any spacecraft size testing of the idea of using superconducting magnetic shields?
So any spacecraft size testing? No, I'm not aware of any spacecraft size testing. Yeah, because the energies are high, and the amount of radiation. About the level of magnetic field is pretty high. Sam Shepard here at Dartmouth at the Thayer School put together a nice design, and he published on that, which was using a toroidal system and superconducting magnets. And he did a lot of the calculations for, how practical that would be. And so I would refer you to that article. I thought it was a pretty good job that he did coming up with an active shielding concept.
All right, if there are no other questions, then we'll go to proceed to the presentation. Ryan, I'll go ahead and make you a co-host, and you can go ahead and share your screen. And then feel free to introduce yourself as well. All right, you should be set.
Give me just 1 second. It's making me sorry about that. I think it kicked me out. You might have to give me the share screen back again. Perfect. Let me know if you guys can see that.
Perfect.
Still can see it?
Yeah.
Awesome. All right. So my name is Ryan Lasinski. I'm an MD PhD student at the West Virginia University School of Medicine. I'm in the second year of my PhD, and I'm studying the development of immunotherapies for the treatment of metastatic osteosarcoma, which is one of those common primary bone tumors. After talking to Joe and others, we really didn't cover any of the spaceflight effects on the immune system throughout the presentation. So I thought it'd be a good opportunity to kind of jump in and give some of my minor expertise on the topic. So just briefly, disclosures. I'm going to give a shameless plug to some of the work I'm doing here at WVU. This work is owned by a biotechnology company known as IceaPath, and this is all patented information as well. So just to give a brief outline of what I'm going to discuss, first, just kind of get everyone on the same page, just to briefly outline the immune system. I'm going to discuss some of those initial clinical observations that were made during space travel. We're then going to review a recently published Nature Scientific Reports paper, kind of look at the key takeaways from that, and then take any questions. So first and foremost, when discussing the immune system, as you may know, already know, it can be divided into two particular portions. We have both the innate as well as the adaptive immune system. And there are cells such as the natural killer cell, which are responsible for communicating between both innate and adaptive immunity. The innate immune system, as you may already know, is responsible for recognizing what are known as pathogen-associated molecular patterns, or PAMPs, and that detection is by what are known as pattern recognition receptors, or PRRs. And it is your innate immune system which is particularly responsible for generating your initial immune response to an infection during those first 7 days. It's important to recognize that not only does the innate immune system include cellular components such as dendritic cells, macrophages, or neutrophils, but it also consists of the epithelial linings that separate and are the barrier between our internal and external environment, such as in your GI tract or throughout your respiratory system. So once again, not only is the innate immune system responsible for generating these nonspecific inflammatory responses, but they're also particularly important for producing cytokines that then interact with portions of the adaptive immune system in order to generate its activation. When looking at that adaptive immune system, as you probably know, it is responsible for our immunological memory. So upon exposure to a pathogen, as you can see here over in this chart, you not only have your innate immune response, we also have this communication to the adaptive immune system. And through this process known as clonal selection, you have the generation of B and T cell specific receptors that can then, upon re-exposure at a later time, recognize this PAMP much quicker and generate a much stronger as well as faster immune response. As has been outlined by Dr. Buckey throughout all of the presentations so far in this course, space travel is associated with distinct and extreme stressors that ultimately influence our physiology. Of those we discussed today, you have exposure to increased radiation, but you're also as likely to see changes within your nutrition, changes in your circadian rhythms, obviously the microgravity effects on bone, which are your most prominent reservoir for immune cells, particularly the progenitor cells. And in these distinct and extreme stressors are ultimately going to result in immune system dysregulation. And it has been seen that this immune system dysregulation can ultimately persist even during 6-month orbital space flight missions. So what are some of those initial clinical observations that were made during space travel? And there's two key observations that were made even back to the Apollo missions. First and foremost, we had saw the reactivation of latent viruses, not just the herpes virus, but even varicella zoster, which is associated with shingles, as well as others. And as you know, after an initial viral infection, such as a herpes virus, you have dormant virus, which remains within your body. And it is a healthy immune system, which is ultimately capable of suppressing latent viral reactivation. However, a common biomarker of particularly a compromised adaptive immune system is reactivation of these latent viruses without a re-exposure event that ultimately results in what appears to be an active infection. This is particularly associated with lack of cytotoxic T lymphocyte function. CD8 positive T lymphocytes are one of the major components of our adaptive immune system. And this is ultimately associated with what is known as a Th2 shift. So a Th2 shift is a less active, less effector cytotoxic T cell, which then allows for the reactivation of these viral components within the immune system. There also was particularly interesting was that there was an increase in what appeared to be allergic symptoms or even skin hypersensitivity reactions that were associated with space travel. And as we'll get to through our discussion in the paper, these are really associated with what is the key common finding with space travel and effects on the immune system, which is what is known as immunosuppression. So what have these previous studies looking at the immune system during space travel have ultimately kind of focused on three key areas. First, they have been responsible for measuring inflammatory cytokines either via isolated plasma or serum. They have attempted transcriptomic assessment of bulk or isolated immune cells through what is known as bulk RNA sequencing. And they'd even done some ex vivo or in vitro functional assessment of cells through immunostimulation assays. However, because most of these previous methods lacked single cell resolution, it's ultimately very difficult to get a comprehensive and functional assessment of all major immune cell subsets individually against one another. And what I mean here is when you're performing assessments such as bulk RNA sequencing, you're taking all peripheral blood cells and isolating them. You're not isolating them from one another. So when you actually isolate the total RNA from this sample, you're getting a mix of RNA from both B cells, T cells, as well as any other cell that would have been in that system. With these single cell resolution techniques, such as flow cytometry, mass cytometry, even single cell sequencing, you're able to isolate the proteins or RNA directly associated with an individual cell within your sample. And this leads us to the paper that I'm going to review today, which is a Nature Scientific Reports titled Human Immune System Adaptations to Simulated Microgravity, Revealed by Single Cell Mass Cytometry. This work by Spatz et al. So kind of giving a brief overview of what this study ultimately detailed. They first isolated PBMCs or peripheral blood mononuclear cells, which would be your immune cells, from 8 healthy patients. And then they took those cells and either exposed them to normal conditions, 1G, or to simulated microgravity for 18 hours through what is known as the rotating wall vessel. And then upon this 18-hour incubation period, they then performed an immunostimulation assay using this CON-A anti-CD28 and expose those cells for 1.5 to 4 hours to stimulated or unstimulated conditions. After this workup, they then perform both mass cytometry as well as RT-PCR to look at the transcriptomic profile as well as proteomic profiles of these cells. And then I really won't detail much of this today, but they also ultimately use a machine learning model through what is known as the elastic net model to correlate their findings from mass cytometry and RT-PCR to particular immune signaling networks to ultimately reveal their major findings. So what is mass cytometry? If you are familiar, more likely familiar with flow cytometry, which is used clinically readily, particularly for not only for diagnosis of certain leukemias, but also to really get a good grasp of what changes are occurring in the immune system as a result of therapy. Mass cytometry is very similar, except the only major difference is you're using what are known as metal labeled antibodies as opposed to fluorescently tagged antibodies. Mass cytometry has a number of pros and cons. The biggest difference between flow and mass cytometry is that mass cytometry, because the stable isotopes of the metals that are actually tagged in these antibodies are very distinct from one another, you lack the fluorescent overlap that is seen, this fluorescent spectral overlap that occurs during flow cytometry. Upon taking PBMCs in a single cell suspension and staining them with these metal labeled antibodies, you then pass them through a nebulizer, perform time of flight mass spectrometry to then ultimately determine the metal mass to intensity profile at the single cell level. The group also, in order to simulate microgravity, used what is known as the rotating wall vessel. The rotating wall vessel was developed by NASA. And in very simple terms, you take a cell culture, media, as well as some microcarrier beads. And through constant rotation of this vessel, you're able to simulate in your cell culture individual cells and often cellular aggregates suspended in what would be considered microgravity. So now I'm looking at some of their key findings that they found in this paper. First and foremost, they used their RT-PCR to look at mRNA transcripts of some common immunostimulation markers. Those markers of immunostimulation include the IL-2 receptor, tumor necrosis factor alpha, CD69, which is a membrane protein that is results in the initial cascade of an inflammatory response on these cells. CCL4, which is your macrophage and inflammatory protein 1 beta, as well as interferon gamma, which is a very common effector cytokine produced by Th1 helper T cells. As you can see here, they highlighted in black your 1G unstimulated after 18 hours, your 1G stimulated, as well as your microgravity stimulated PBMCs. And as you can see, the major finding here is that most, if not all, of these immunostimulation markers are drastically suppressed as a result after exposure to microgravity. Then moving to this machine learning elastic net model, they then ultimately, using the cellular populations identified via mass cytometry and some of their RT-PCR findings, then correlated immune cell signaling pathways to one another. And as you can see here, it's kind of confusing, but the an increasing EN coefficient ultimately means that is likely suppressed from the 1G condition versus a decreased EN coefficient is associated with an increased activation or a decreasing EN coefficient. As you can see, many of these same markers, when isolated to particular cell populations, as you can see in the red, not only are the proteins suppressed, but we also see suppression of the transcription factors such as STAT5 and STAT1 that are associated with these immune pathways. Most importantly, the group ultimately determined that within your T regulatory cell population, you actually had increased STAT5 signaling. This STAT5 signaling was ultimately not related to IL-2 receptor availability, and which I'll show in a later figure. IL-2 binds to the IL-2 receptor and drives increase in STAT5, and is that increase in STAT5 which is ultimately allows these T regulatory cells to not only proliferate but then ultimately have immunosuppressive function. So kind of some of the conclusions or key takeaways from this paper, that after their in-depth functional assessment of the microgravity's effects on the peripheral immune system, they ultimately determined profound and cell-specific immune alterations. Not only did microgravity suppress some of the key aspects associated with CD4, NK, and CD8 positive T cell immune activation, as seen through analysis not only of signaling pathways, but receptors on these cells. We also see enhanced signaling responses, particularly in Tregs, that would allow them to have a much higher immunosuppressive capacity. This increased STAT5 signaling, as I kind of discussed, is what they believe is the immune change that's occurring as a result of microgravity exposure that allows for increased immunosuppression within astronauts. And as I previously discussed, this is not downstream of IL-2 signaling, so there is a different pathway that is resulting in this STAT5 upregulation to cause immunosuppression. And as you can see, due to the highly complex immune modulation that occurs as a result of microgravity, it is vastly important to use single cell techniques such as mass cytometry or flow cytometry, as this STAT5 upregulation, particularly in Tregs, would have likely been overshadowed in a bulk assessment of these cells, considering that it is vastly downregulated in almost all other cell populations. So as you can see here, the normal Treg, you have a dysfunctional Treg. In order for that Treg to ultimately become functional and provide an immunosuppressive effect, the most common mechanism and pathways, you have the IL-2 cytokine produced by macrophages as well as dendritic cells binding to the IL-2 receptor, resulting in the phosphorylation of STAT5. This is a feedback mechanism that allows the increased production of IL-2 receptor on the surface of these Tregs, but it is then this phosphorylated STAT5 which can then act as a transcription factor to ultimately increase the immunosuppressive capacity of Tregs. However, what this group ultimately determined that because there was no changes in the IL-2 receptor on the surface of these cells, there's likely a different mechanism that is causing this phosphorylated STAT5 increase within the Treg population. When looking at this study, obviously it has its own limitations. They used the microgravity model system through this rotating wall vessel, which ultimately limits its generalizability. However, a lot of the markers that were used in this study were ultimately correlated to previous studies examining a very similar topic, and their results ultimately correlated. So it gives some credibility to using this rotating wall vessel. They also only looked at a single microgravity exposure time point, and that was 18 hours. I would have really liked to see them extend the exposure to see some long-term effects and whether or not this STAT5 increase in Tregs persists. And then once again, they only used one single stimulation condition. The CON-A anti-CD28 antibody is a very common pleomorphic and pleiotropic way to activate the peripheral immune system. However, it would be very interesting to see if they'd use a different stimulation method, such as LPS, that would actually really mimic some form of a bacterial or viral infection, whether or not that would have the same effects. And then once again, kind of the key takeaway here is that spaceflight is ultimately associated with increased immunosuppression, and that is what is implicated in some of those latent viral reactivations seen on space missions. What I find particularly interesting and kind of related to some of the research I'm doing is obviously cancer is highly associated with increased immunosuppression, not only within the local tumor microenvironment, but also systemically. Osteosarcoma, which is a bone tumor that metastasizes to the lung, is particularly associated with drastic increase in immunosuppression system-wide, which is why it is ultimately able to metastasize from a very harsh environment of the bone to something such as the lung. Some of the work that I've done at the WVU School of Medicine is generating this novel immunotherapeutic, which I call IL-12NS. We particularly take interleukin-12, which is an immunostimulatory cytokine, and load it into PLGA nanospheres for systemic delivery to prevent metastatic disease. As you can see here, here's all the worldwide patents that are associated with this technology. But Dr. Buckey, if you know anyone who's doing some of this work on immunosuppression during spaceflight, we hope to be in a human clinical trial by the end of next year, testing our novel immunotherapeutics ability to suppress metastatic disease through very long-term low immunostimulation. And it would be very interesting to see whether or not this interleukin-12 loaded PLGA nanoparticle can be used to kind of counteract the immunosuppression that is seen during spaceflight. If anyone else is interested to see some of the other countermeasures that have been used in order to kind of block the immunosuppression that is occurring in these patients, you can go ahead and take a look at this review by Crucian et al. And with that, I'll take any questions and greatly appreciate the opportunity.
Oh, hey Ryan, how's it going?
How are you?
Good. I was curious, were there any measures taken with that study to like better mimic the in vivo environment? I know, I mean, even with like regular old cancer research on the ground, it's hard to really take those outcomes and translate into what happens in the body because of the vast differences like pressure, 3D environment, other cells, structure. So yeah, if you could comment on that.
For sure. Yeah. I mean, model systems are model systems for a reason. At the end of the day, it would be best to isolate some human peripheral blood mononuclear cells from astronauts returning from space flight. Interestingly enough, some of these single cell techniques are pretty revolutionary and new. And they really haven't made their way into some of the actually redoing some of the previous experiments that use bulk RNA sequencing or bulk analysis. So what was nice is that some of their findings did directly correlate to those previous bulk analysis. There were actually cells isolated from astronauts. So the next step moving forward, obviously, would then to perform this similar single cell mass cytometry on cells isolated from astronauts, and then obviously see if their results correlate directly. But because there is no direct correlate, that data does not exist just yet. Also, too, it's very difficult for immune cells. A lot of the samples that are obviously collected during space travel have to be stored and frozen. You can't be doing these experiments actually on the space shuttle themselves. Immune cells are highly affected by freeze-thaw cycles, as opposed to other cells such as cancerous cells or proteins. Cells are very, very, very sensitive to freeze thawing on ice. So just that alone would probably mask most of the changes that you would see in these signaling pathways, just by having to isolate cells from a frozen sample. So,
yeah, thanks.
No problem. You guys can just keep them rolling. Whoever's next, jump on in.
Go for it, Nicholas.
Thanks. Hey, Ryan, thank you. Actually, like thinking about it, it kind of makes sense that a rotating chamber might be more like a better model, because, you know, like hemodynamically, like blood is going to be moving around even if there's no like downward G-force. What do you think about like the lack of a consistent down vector? Is it that like mechanistically triggers all of this? Do you think it's just stress, or like something in particular about like the lack of consistent?
Right. Yeah. So I think maybe not particularly for this paper. I think there's the immune system changes are first born by the actual changes that occur because of changes in bone. So I think a lot of those original findings, because they really weren't aware of the bone changes, and they really weren't aware back in the day how much nutrition and the right mixture of amino acids and proteins within your diet can ultimately have a very large effect on immune cell function. I think those original studies, kind of what they were seeing might have been more so related just to simply lack of great nutrition or lack of exercise and bone, and really lack of development of those progenitor immune cells into functional effector cells, which is also seen in cancer, is also seen in HIV and other infectious diseases as well. But yeah, so particularly here, I'm not sure, honestly. It's kind of crazy to think about that a particular single transcription factor could ultimately be affected by simulated microgravity, and have cellular specific changes, right? So STAT5 was increased in all or decreased in all other cell populations. However, it was particularly increased in Tregs. And that might be a result of a more global effect on all cells. T regulatory cells use STAT5 for a number of things. Their proliferation, differentiation, and ultimately immunosuppressive function is directed by STAT5. So it might just kind of be a very almost a niche example, just because it's kind of what is there is going to function, right? So if you have increased STAT5 already and microgravity doesn't seem to decrease it because it is already elevated in that cell population, is why you see it's almost like a war of attrition. What's left over? Tregs with high STAT5, and they're just going to function as they have no idea they're in microgravity, right? So I think that might be the causative reason.
Cool. Thanks.
No problem.
Thank you so much, Ryan. It was a great
Thanks. Appreciate it.
presentation. Really nice information and everything. I just had a question. You mentioned that you wanted to go into human-based trials, and I know that your methods that you were using, or that the company was using, was regarding, I think it was 18-hour periods for microgravity exposure. How would you, if you know any of this information, how would you kind of apply that to a human? Would you look at those same time frames, or how would you expose them to microgravity in a short duration space mission, or kind of how, if you have any insight to that, how would you visualize that in a human?
Right. Yeah. So right now, currently, the entire mechanism of our immunotherapy is that the IL-12 is actually released from the polymeric shell capsule of the nanosphere over time. So you can take one single dose, and that single dose will then deliver interleukin 12 over a 14 to 17 day period to kind of cause everlasting immunostimulation at particularly kind of low, safe, and healthy levels. In a clinical trial in the future, because of knowing that, I probably would suggest a single dose injection, especially on a short duration flight, before, and then ultimately measuring the response and effects that would occur upon landing afterwards. For a longer duration mission, because this is an intravenous injection, I'm not exactly sure how you would continue the therapy over time, but I think that these kind of forms of either kind of prophylactic therapy that can be initiated in order to prevent, especially if you know someone like, hey, I had chickenpox when I was a kid, I'm at high risk for varicella zoster virus reactivation and development of shingles. This could be something, and IL-12 has been shown in numerous clinical trials to not only have anti-cancer effects, but also antiviral as well as antibacterial effects as well.
Thank you.
All right, thank you, Ryan, for your presentation today, and thank you, Dr. Buckey, for joining. I think that'll wrap up today's session since we're already at time, but we look forward to seeing you all next week. And please feel free to reach out if you have any questions or any suggestions or anything like that.
Thank you.
Greatly appreciate it, guys. Take care.
Good night.
Thank you.
Thank you so much.